Okay. Almost 20 years ago, I learned that if you are a student of technology, you know solutions. Everybody's been taught solutions. They might not know what the problem is, and they might not know what the criteria for a good solution is, but they'll know solutions. And so like a good student of technology myself, I'll present a solution. I probably don't have a clue as to what the problem is, and I might not know what's relevant for the whether it's good or not. So let's talk about it. And it's not a new solution. So that's probably the good thing about the whole thing. Okay, and there's this joint work with Hannu-Matti, Järvinen. Talks over years we've had, and I just wrote them up for the position paper. Okay, not that way. Okay. A friend of mine way back said that software engineering is not a stable area of engineering, simply because you cannot get liability insurance for software. Nowadays you can, which shows that some people are willing to take risks with their money, namely the insurance companies. But the issue he had was that he had a background in something what Ines told this morning in shipbuilding, and his idea was that if you design a ship, it really doesn't matter how good the ship is if you don't do it according to the specifications of the insurance companies that will give it a liability insurance, because then it will never get built if it's not done according to the specification of the insurance companies. And so the point was that those guys will need ways of limiting the risk they will have when the thing is actually built and is floating on the sea and may hit rocks and whatever. And so the point was that those kinds of things were missing at that point in time, and I don't think we're that much closer to the situation that big firms would actually have real interest in putting money, insurance money, risking their money for liability insurance for software. Okay, so that's one of the reasons why I talked about prediction of the properties of software engineering artifacts yesterday. Okay, any theory by definition will limit the domain of its discourse. So you want to say what's in the thing and what's out of it, and so that's one of the exercises you need to do when you come up with engineering theory. If it's concisely formulated, so much the better. Then it's tangible, it's written down, it's better for the human mind to understand, because humans don't understand things which consist of more than about 6 things or 7 things. So much the better. It should be understandable, not necessarily so that everybody understands it, but there should be a way of understanding it, or at least having some kind of a grasp of it, if not a complete understanding. And it need not be final. It will develop, obviously. The example we had with Pontus in the first presentation of Maxwell equations, as far as I understand, they break down with quantum mechanics. You will have effects like the electron in a hydrogen atom in a accelerated motion. That would be, according to Maxwell's equations, would start losing energy profusely. But the quantum effects will kick in and not allow it. And so it will break down. But the nice thing about there is then, okay, I've moved over too far, that the thing should be such that it could be refined it should be applicable at various resolutions. That you could have a bulk thing and then look more closely at certain more refined thing and then go even deeper and deeper. So the refinability is, in my opinion, important, as the Maxwell's equations can be sort of refined up to the point where the quantum physics hit in. Okay, and my big cry of yesterday, it should be able to predict the properties of artifacts. Should be able to be used like the Maxwell's equation to predict the things that the engineer produces. Okay, and so my small point in the paper was that software engineering artifacts are kind of computations. So they start at the low level at computations, something happening in the machine, changes of state, transformation of state at that level. Then there will be software engineering artifacts called programs that will be descriptions of the computations that can occur, that are supposed to be possible. And then there will be descriptions of programs, documents describing what the programs should do or will do. And there will be transformations of programs, which will be software engineering processes, and again transforming artifacts on the way, and transformations of documents, of course, also on the way. So the sort of inductive idea here is that the software engineering artifacts are computations or descriptions of such and processes such that transform a certain state, and then you apply this recursively on each level. And it's not, I don't think this is a big idea, this is just sort of lumping together things that are sort of obvious. Okay, so the age-old thing about thinking about these things is states and transformations. So you start with states of the thing and you talk about transformations, and so you can pick your theory, you can pick your language, you can describe your particular artifacts and what the transformations are and how you should do them. And obviously there's lots of competing theories on each level and on each particular kind of process you're interested. So that's it. There's lots of them around. Nasty thing is that they are incompatible, and the nasty thing is that people don't know what the next guy has done. Yes, an important point that was mentioned today, and that's nasty, and we should do something about it. Not necessarily the general theory need not be able to do that thing, but something should be done about that. If you take the Maxwell's equations and think about what the analogy there could bring in here, is that they talk about bulk properties like currents and not potential, but currents at least, and charges, distributions and movement of charges, and so the question is, what would be the relevant bulk properties of interest for the artifacts of your choice? What kind of things are sort of describing the relevant properties of the artifacts you have of interest? And again, analogy there, what would be the fields and the potentials, the kind of things that the Maxwell's equations boil down to when actually used most of the time? What would be the kind of things that sort of make the computation, the trajectories of the charges, if you want to think of it in that way, in Maxwell's theory? How do they affect? What are the concepts that affect the software engineering artifacts? The kinds of things that you want to look at. Okay, so that was about states and transformations. So there's a bunch of things that you can choose from there. Well, the question was posed, what would be a proper language? Well, my solution, I don't know if it's that much of Hannu-Matti Järvinen, my co-author, but my solution would be mathematics and logic. Not that I'm very good at it, or not that I'm sort of very fond of it, but it's the in a sense the poor thing but mine own. The best thing that the human race has sort of come up with, which to describe things that you want to control. So the poor thing but mine own is from Eugene O'Neill's play Long Day's Journey into Night. And no, I haven't actually checked that it's written like this, so if you find me wrong, tell me. Okay, we are interested in Hannu-Matti about things like unity and disco of Reino Kurkisuonio, which are interesting things because they do have a refinability ability. So you can refine descriptions of processes while preserving their properties to given extent, some extent, and so they that's something we think is going to be very important to be able to preserve things while refining. Disco is actually kind of subset of temporological actions. There's an immediate translation of a disco thing into a temporological action formula, and so you can do not everything that you can with temporological action, but you have a restricted subset of temporological actions that you can play with. And my background is in Petrinets, which is yet another way of thinking about sort of states and transformations, and they bring in something slightly different than the logics and programming languages like this. So those are our preferences, but of course everybody else will have their own preferences. And so whether the fear is whether we can achieve a case where you can combine and interwork with all of those, that would be an interesting thing. So my points are about there. Okay, so refinement, in my opinion, is important to remember. Okay, the other thing I think is important to remember is that for okay, the way some people in Petrinet community way back put it, we are teaching our students to be brain damaged by letting them start with a programming language of sequential kind. Right. So yes, everybody will be sitting on top of the world, only one thing happening at a time. But please remember that in all the relevant cases we've been talking about here, things happen concurrently. So different things happening at the same time, no necessary order on the things either. So don't sort of formalize things to the point of having sequential things. Remember concurrency. Okay, and yes, that's enough for me.
Thank you very much.